Right now, more than 25 billion kilometers from where you're sitting, a machine humanity built before the invention of the personal computer is quietly picking up something that shouldn't exist by most of the assumptions scientists held only a few decades ago. Not a voice, not a message from another world, something stranger and, in its own way, more profound. NASA has confirmed that Voyager 1 is receiving signals from deep interstellar space, a region no human instrument had ever touched until this single spacecraft crossed into it. And what those signals are revealing is rewriting what we thought we understood about the space between the stars. To understand why this moment matters, you have to go back to a decision made in 1977, when Voyager 1 launched with a mission that was supposed to last 5 years. Fly past Jupiter, fly past Saturn, send back pictures, and quietly retire. Nobody on the engineering team expected the spacecraft to still be operational nearly half a century later, and almost nobody imagined it would end up doing some of its most important work only after leaving the solar system behind entirely. Yet, that is exactly what happened. The mission that was designed to study planets became, almost by accident, humanity's only working instrument for directly sampling the environment between stars. For decades, the assumption inside the scientific community was straightforward. The sun's influence, carried outward by a constant stream of charged particles called the solar wind, would gradually fade the farther you traveled from it. Scientists pictured this transition as gentle, blurry, and slow, a soft handoff rather than a hard edge. There was no way to test that assumption directly because no spacecraft had ever traveled far enough to check. Voyager 1 changed that on August 25, 2012, when its instruments detected an abrupt drop in solar particles paired with a sudden spike in high-energy particles arriving from deep in the galaxy. It wasn't gradual. It was almost like the spacecraft had struck an invisible wall. Voyager 1 had crossed the heliopause, the true boundary where the sun's bubble of influence ends and interstellar space begins. The crossing alone would have been enough to make Voyager 1 historic. But it's what happened afterward that connects directly to the signals NASA is confirming today. Once outside the heliosphere, one particular instrument on board, the plasma wave subsystem, kept working, and it started picking up something nobody expected to hear at all. Interstellar space was supposed to be silent, empty, a vacuum in every sense of the word, with nothing to vibrate, nothing to resonate, nothing to produce anything resembling a signal. Instead, Voyager 1's instruments detected a persistent, faint oscillation, a tone sitting at roughly 3 kilohertz, far below what the human ear can hear on its own, but perfectly capable of being converted into audible sound once translated by scientists on Earth. That tone lasted for years, not seconds, not minutes. Years. And it wasn't noise. It was structure. It was data. It was, in the truest sense of the phrase NASA itself has used, the sound of interstellar space. What Voyager 1 is actually detecting is something called interstellar plasma oscillations, waves moving through the thin scattering of charged particles that fill the space between star systems. These aren't radio broadcasts, and they aren't anything resembling communication in the way we imagine it in movies. They are physical vibrations in extremely low-density plasma, and the reason they matter so much is that they let scientists measure something that would otherwise be almost completely invisible from Earth: the density of the material drifting through this galaxy far beyond our sun's reach. Think about what that actually means. For most of human history, the space between stars was treated as an assumption, a blank space filled in by theoretical models because nobody had ever been far enough away to check. Voyager 1 turned that blank space into measured, confirmed data. By analyzing the frequency of these plasma waves, scientists can calculate how many electrons exist per cubic centimeter in the region Voyager 1 is currently passing through. And that number has already forced multiple revisions to how astronomers model the boundary of our solar system. That scarcity is exactly what makes every confirmed signal Voyager 1 sends back so significant. This isn't a routine data stream from a modern satellite that could easily be replaced or supplemented by a dozen similar missions. It's an irreplaceable, increasingly fragile connection to a part of the universe that remains almost entirely unexplored by any other means. Every plasma wave event NASA confirms, every density spike traced back to a solar storm from a year earlier, every subtle shift in the strength of the interstellar magnetic field adds a small but permanent piece to a picture that took humanity nearly 50 years and one extraordinarily lucky planetary alignment to even begin drawing. There's also something worth acknowledging about how these confirmations keep circulating years after the actual detection events occurred. Interstellar plasma wave data from Voyager 1 isn't the kind of information that gets fully analyzed the moment it arrives. Scientists have continued revisiting archived readings, applying new models and new analytical techniques to signals recorded years earlier, sometimes uncovering patterns or confirming density measurements that weren't fully understood the first time around. That means NASA's confirmation of these interstellar signals isn't a single isolated headline. It's part of an ongoing process, one where old data keeps yielding new insight as scientific understanding of the interstellar medium slowly matures around it. Meanwhile, the spacecraft responsible for all of this keeps moving outward, at roughly 17 kilometers every single second, carrying a golden record bolted to its side containing sounds, images, and greetings meant to represent life on Earth to anyone or anything that might one day find it. It is a strange kind of coincidence that the same spacecraft carrying humanity's introduction to the universe is also the one currently listening to the universe's own quiet signal back. An ambient hum in the plasma between stars that has nothing to do with intention or communication, yet reveals more about our galactic neighborhood than any telescope on Earth ever could. Engineers currently believe at least one instrument, potentially including the plasma wave subsystem, could continue functioning into the next decade if power conservation efforts hold and no critical hardware failure occurs first. Nothing about that timeline is guaranteed. Mission leaders have been candid about the fact that a single unexpected failure, whether from a frozen propellant line or an antenna drifting out of alignment, could end the mission with almost no warning at all. But for now, today, in this exact moment, a machine older than the personal computer, running on a fraction of the power inside a household light bulb, sitting so far away, that its own signals need nearly a full day just to reach us, is still listening to something no human instrument had ever heard before it got there. To really appreciate why this specific confirmation carries so much weight, it helps to understand what scientists were actually expecting before Voyager 1 crossed the heliopause in the first place. Ground-based models built throughout the 20th century treated interstellar space almost like an afterthought, a placeholder region defined mostly by what it wasn't. It wasn't the solar wind, it wasn't a planet's magnetosphere. Beyond that, there wasn't much confidence about what it actually contained, because no instrument had ever been positioned to measure it directly. Every equation used to describe the boundary of the heliosphere prior to 2012 was, in a sense, an educated guess extrapolated from indirect observations, cosmic ray measurements taken from Earth, and theoretical modeling of how stellar winds should behave based on physics that worked well everywhere else it had been tested. Voyager 1's crossing didn't just add a new data point. It replaced years of extrapolation with direct physical measurement, and in doing so, exposed just how much of the earlier picture had been built on assumption rather than evidence. That shift, from assumption to measurement, is really the through line connecting the initial 2012 heliopause crossing to the ongoing confirmations happening now. Scientists didn't stop paying attention to Voyager 1 once the boundary crossing itself was confirmed. If anything, that moment marked the beginning of a much longer, quieter phase of the mission, one focused less on a single dramatic threshold and more on the slow accumulation of readings from a region nobody had ever sampled before. Each new plasma wave detection functions almost like a single brushstroke in an enormous, unfinished painting of what lies just beyond the solar system's edge. No single signal tells the whole story on its own. It's the pattern across years of data that has allowed scientists to build something resembling an actual evidence-based model of the local interstellar medium. It's also worth noting how unusual it is for a single instrument on a single aging spacecraft to remain the sole source of this kind of data for over a decade. In most areas of astrophysics, new missions, new telescopes, and new instruments regularly replace or supplement older data sources, refining measurements and cross-checking results against multiple independent tools. Interstellar plasma wave detection doesn't have that luxury. There is no fleet of interstellar probes quietly gathering competing measurements from other directions. There is Voyager 1 and there is Voyager 2, trailing behind at a different angle, and that's essentially the entire observational toolkit humanity currently has for this specific region of space. Every confirmed signal carries outsized scientific weight simply because there's nothing else available to compare it against directly. This scarcity also explains why NASA's science teams have treated even small, incremental confirmations with the level of seriousness usually reserved for larger discoveries. A subtle shift in plasma density, something that might seem like a minor technical footnote in almost any other field, becomes meaningful here precisely because it's one of the only direct measurements of its kind that exists anywhere. Scientists studying the interstellar medium from Earth-based observatories can infer certain properties indirectly, using starlight absorption and other remote techniques. But those methods provide broad, average pictures of interstellar conditions across vast regions of the galaxy. Voyager 1 provides something entirely different, a precise, localized measurement from one specific point in space, gathered in real time by an instrument that is physically present in the environment it's studying, rather than observing it from a comfortable distance of several light years away. There's a kind of quiet irony sitting underneath all of this, too. Voyager 1 was never meant to become an interstellar science instrument. Every part of its plasma wave subsystem was engineered, tested, and calibrated for a completely different job. Studying plasma conditions in the vicinity of Jupiter and Saturn, where particle densities and electromagnetic conditions are dramatically different from the thin, cold plasma drifting between stars. Nobody who built that instrument in the 1970s could have designed it specifically for this purpose, because nobody at the time even had a clear picture of what interstellar plasma conditions would actually look like up close. And yet, decades later, that same piece of 1970s engineering has become one of the most scientifically valuable instruments currently operating anywhere in the solar system, simply by virtue of being in the one place nothing else has ever reached. None of this diminishes how fragile the entire situation remains. Every additional year that NASA continues confirming new interstellar signals from Voyager 1 is, in a very real sense, borrowed time. The spacecraft's power supply continues to shrink, its structural components continue to age in an environment of extreme cold and constant low-level radiation exposure, and its ability to communicate with Earth depends on delicate alignment between its antenna and a planet that, from Voyager 1's current vantage point, is little more than a faint point of light lost among billions of others. Engineers have described the ongoing effort to keep the spacecraft's most valuable instruments alive as a continuous balancing act, one where a single unexpected hardware failure could end this specific stream of interstellar data permanently, with no possibility of sending a replacement mission to pick up where it left off. That fragility is part of why each new confirmation matters so much in the moment it happens. Nobody involved in this mission is under the illusion that Voyager 1 will continue sending back interstellar plasma data indefinitely. Every signal that reaches Earth today is treated as one that might not be followed by another, which is exactly why scientists have been so thorough about analyzing, cross-checking, and eventually confirming what these signals actually represent before publicly attributing them to genuine interstellar phenomena rather than instrument noise. There simply isn't room for a hasty or premature announcement when the underlying instrument producing the data could fall silent at any point without warning. Perhaps the most striking part of this entire story is how ordinary it has quietly become for something so extraordinary to keep happening. A machine built before most currently practicing astrophysicists were even born is still actively producing new scientific insight, still forcing revisions to textbook models, and still doing so from a region of space that, for the entire history of human civilization before 2012, existed only in theory. There is no equivalent example anywhere else in the history of space exploration. A single instrument, still functioning, still relevant, still confirmed to be capturing real physical phenomena from a part of the universe nothing else has ever directly sampled. And so the story keeps unfolding in exactly the way it has for over a decade now, quietly, patiently, one confirmed signal at a time. Somewhere out past the edge of the sun's reach, a 50-year-old spacecraft, running on a power source weaker than a household appliance, continues listening to the faint, persistent hum of interstellar plasma drifting through the space between the stars. And it is still finding a way, against every original expectation placed on it, to tell us what that silence actually sounds like.